At exactly 8:30 in the morning on November 22nd, NASA published a new series of enhanced images of the interstellar object known as 3I Atlas. The release was quiet. No press briefing, no formal announcement. Just a silent upload to their public repository followed by a short technical note. But within minutes, astronomers began to notice something unusual. The new frames did not match the predicted behaviour for an object of its size, shape or temperature. They revealed structures that looked stable in an environment where nothing should remain stable at all. So before we begin, take a slow breath. Let your focus settle. There is no speculation here, only what the data shows and the questions that naturally follow from it. Drop a comment below and tell us where in the world you're watching from and what time it is right now. Now let's walk through the 10 findings from NASA's new imagery release and see whether 3I Atlas is following physics as we know it or quietly challenging the rules. NASA's newly released images show something that immediately stands apart from typical comet behaviour, a near-perfect symmetry in the plasma envelope surrounding 3I Atlas. In natural comet environments, this symmetry rarely lasts longer than a few minutes. The solar wind constantly sculpts and reshapes the ionized material, producing uneven layers, turbulent arcs, or distorted halos that respond rapidly to changing conditions. But in these new frames, the halo around 3I Atlas appears almost geometrically smooth. It maintains a consistent curvature from one exposure to the next, as if the surrounding particles are being guided by a stable internal pattern, rather than drifting freely. This is unusual because the nucleus is small and rotating. Small objects in plasma environments typically generate messy, unstable fields. Their low gravity and inconsistent outgassing allow the solar wind to disrupt them easily. Yet here we see a structure that behaves more like a self-organizing system. Plasma that should disperse instead settles into orderly layers. Charged dust that should scatter instead aligns along quiet gradients. One explanation is that the nucleus releases gas in a more uniform manner than other comets. But even that does not fully describe what we see. Uniform outgassing alone cannot create a halo that remains stable across changing solar wind speeds. Another idea is that the surrounding environment contains electromagnetic pockets that lock particles into specific paths. This happens occasionally around bodies with magnetic fields, but 3I Atlas is too small to carry a strong intrinsic field on its own. The emerging idea among researchers is that the symmetry might result from an interplay of ion currents, solar wind deflection, and unusually efficient charge separation. The outcome is a layered shell that appears sculpted rather than random. Nothing about this breaks physics, but it pushes our understanding of how interstellar objects preserve structure under extreme conditions. One of the most striking findings from the new image set is the persistent orientation of a linear structure extending outward from the nucleus. In natural comets, such features shift frequently because the rotational movement changes the direction and angle of material escaping the surface. Jets curve, widen, or distort as rotation carries them into different light angles. But in the NASA release, the outer stream stays locked into the same position across multiple rotation phases. This raises immediate questions. If the nucleus rotates once every 16 hours, why does the stream not follow that movement? A persistent alignment suggests that something beyond simple outgassing keeps it steady. Scientists exploring this have proposed two families of explanations. The first is rooted in surface features. If the jet originates from a region aligned with a magnetic anomaly, or a deep fissure that faces a stable direction, it might appear fixed. But this becomes difficult to reconcile with the rotation. Even deeply embedded vents move with the nucleus. The second explanation involves the environment around the object. If the surrounding plasma shell carries an organized electric field, it could guide the escaping ions along a specific direction, regardless of the surface rotation. This is consistent with laboratory plasma behavior, where field lines dictate flow orientation. But sustaining such organization over interstellar distances and under active solar wind pressure is unusual. What makes this more complex is that the outer stream maintains its shape without broadening. In the vacuum of space, ion streams typically spread unless confined by an external force. Yet this stream stays narrow, suggesting that the surrounding environment is shaping it as much as the nucleus is. The fixed orientation does not indicate anything artificial, but it reveals that 3I Atlas operates within a plasma environment that behaves more like a controlled flow system than a chaotic cloud. The infrared data released alongside the new images has brought forward one of the most puzzling observations so far. Despite approaching the Sun at a distance where most comets begin heating unevenly, the temperature map of 3I Atlas shows a surprisingly uniform distribution. Standard comet behavior involves areas of rapid warming where fresh ice becomes exposed, followed by irregular cooling phases as dust layers shift. But here the temperatures remain consistently lower than expected and lack the extreme contrast typical of sublimation-driven surfaces. This uniformity suggests a surface with unusually stable thermal properties. One theory proposed by thermal modelers is that the object is coated with material that has a low absorption profile, something that reflects most solar energy rather than absorbing it. But even highly reflective materials tend to warm unevenly across irregular surfaces. Another idea is that the nucleus has a thick, insulating layer preventing heat from penetrating deeper layers. This could explain the cold readings, but would not explain why all regions appear similarly cool. What complicates the picture further is the low thermal inertia implied by the data. The surface adjusts slowly to temperature changes, yet the distribution remains even. In natural comets, slow thermal response usually results in patchy heating. Here the patches are absent. The most grounded interpretation is that the object releases gas from small, deeply embedded pockets instead of broad surface areas. This could allow the surface to remain cool while sublimation occurs internally. But even this model struggles to reproduce the smooth temperature profile seen in the NASA images. The infrared readings do not violate physical laws. They simply indicate an object whose surface behaves more like a regulated system than a chaotic mixture of ice and dust. It hints at a structure that manages heat in a way we do not fully understand. One of the more subtle anomalies in NASA's release is the brightness plateau observed across several days of monitoring. In all known comets, brightness increases steadily as the object approaches the Sun. This is because sublimation intensifies, releasing more dust and gas that reflect sunlight. But the observations of 3I Atlas reveal an unexpected flattening in the brightness curve. Instead of rising, the curve levels off and remains steady despite the increasing solar energy it receives. Brightness plateaus can happen, but they typically occur during temporary shutdowns of sublimation, when dust layers shift to cover active regions. These shutdowns are brief and often produce sudden dips followed by rapid increases. What we see here, however, is a sustained plateau without volatility. The most conventional explanation is that the object has entered a phase where new sublimation does not outpace dust removal or plasma stripping. But this does not fully align with the timing. During the period captured by NASA, the solar wind intensity was declining, meaning stripping should have reduced. Another possibility considered by astronomers is that the object contains very little surface ice. If sublimation is not the primary driver of brightness, then the plateau may represent a baseline reflectivity of dust already released. But this conflicts with the fact that other measurements confirm ongoing gas emissions. One particularly intriguing idea is that the brightness plateau results from a balance between outgassing and plasma confinement. If charged dust becomes trapped in the object's magnetic shell, it might contribute to a stable brightness level independent of sublimation changes. Under this scenario, the observed light would come from long-lived particles suspended in the surrounding environment rather than continuously escaping from the surface. The plateau does not suggest anything unnatural. It simply points toward a process where dust production stabilizes under the influence of plasma behavior rather than classical sublimation dynamics. NASA's magnetohydrodynamic models included in the new release suggest that the magnetic shell surrounding 3I Atlas is larger and more structured than first believed. Natural comets develop magnetized plasma regions when the solar wind interacts with escaping gas. These regions are typically proportional to the rate of outgassing. The stronger the gas release, the larger the magnetic bubble. But for 3I Atlas, the shell appears oversized relative to the observed rate of mass loss. This mismatch has led researchers to examine which factors could amplify the magnetic environment without increasing gas production. One candidate is dust-dominated ionization. If the object releases charged dust grains rather than primarily gas, the interaction with the solar wind could create a stronger induced magnetic signature. Dust grains hold charge effectively and can create extended electromagnetic boundaries. Another consideration is the geometry of the nucleus. If the object has surface regions that release ions in narrow concentrated channels, The resulting plasma could form coherent fields that extend farther than typical diffuse outflows. This could produce a structured shell that persists even when the nucleus is not highly active. The surprising stability of the magnetic boundary is also noteworthy. In natural systems, these boundaries fluctuate constantly in response to solar wind pressure, but NASA's frames show a boundary that shifts slowly and retains its form longer than expected. This suggests that the object's plasma environment interacts with the solar wind in a more organised way than simple models allow. While none of this implies anything artificial, the amplified magnetic shell indicates that 3I Atlas operates in a complex electromagnetic state. Its interaction with the Sun produces a magnetic envelope that behaves more like a stabilised field than the chaotic boundaries commonly seen in cometary environments. This pushes our understanding of how interstellar objects adapt to solar conditions. Another unusual feature in NASA's latest imagery is the lack of visible turbulence near the nucleus despite the rotation of 3I Atlas. Typically, when a comet rotates, gas escaping from vents collides with solar wind streams and forms chaotic mixing zones. These regions show visible distortions, curls, and irregular boundaries where fresh ionized material interacts with the surrounding plasma. But the region near the nucleus of 3I Atlas appears calm. The transitions between surface jets and the outer environment look smooth and controlled. This observation has prompted researchers to reconsider how the object's plasma environment might be dampening turbulence. One idea is that the slow rotation rate reduces velocity differences at the boundary, but even slow rotating nuclei produce disturbances because the direction of released gas shifts with rotation. The 16-hour rotation period should still create notable variability, yet NASA's images show smooth gradients instead. Another theory involves electromagnetic confinement. If the plasma surrounding the object carries organised electric fields, it may guide ions along defined paths, preventing them from colliding chaotically with other streams. In laboratory plasma experiments, similar behaviour occurs when field lines confine charged particles along narrow routes. The environment around 3I Atlas may be producing such channels naturally due to interactions between solar wind particles and dust-laden ion flows. Another possibility is that the majority of material escaping the nucleus is not travelling outward with strong momentum. Instead, it may be ionized so rapidly that it becomes entrained immediately into the surrounding plasma. If this is the case, turbulence would be minimized because the escaping material never forms dense jets that collide with external flows. All interpretations remain grounded in physical processes, but the lack of turbulence suggests that the environment around 3I Atlas behaves more like a regulated plasma system than a typical rotating comet boundary.